All right, we're going to continue looking at telescopes in Chapter 5. Now, 50 years or so ago, astronomers would record images from telescopes on film, old-timey camera type deal. But in the more modern era, we have digital photography, which makes use of something called charged coupled devices, CCDs. And here you can see a computer chip that is a CCD, and here they've taken one little segment here and they've blown it up. And you can see the scale here. I don't know if you can read this or not, but from here to here is 1 millimeter in size. So this is a fraction of a millimeter. So we've zoomed in really a lot to see this. And you can see here are some wires, and then each of these is representing basically little pixels that are sensors that light falls on, and the intensity of the light is recorded and translated into a number. So more intense light would be a bigger number, for example. So if it's a certain level of brightness, it might record a 2. And if it's another level of brightness, it might record a 5. And it can actually do this for multiple colors at the same time. So it could record, all right, so I'm seeing a 2 of red and a 5 of green and a 3 of blue. And then, you combine those and you get a particular color that's a combination of those colors. But the key thing is that the intensity of these different colors are converted into numbers. Another word for number is digit. That's why it's called digital photography. And digital photography makes use of these CCDs to convert the information stored in the light into numbers that can then be reproduced on a computer screen or printed out or whatever. And CCDs are much, much better than film now. One, they're much higher resolution. It wasn't always the case, but higher resolution images mean there's more detail in the image. So a CCD, a modern CCD, can capture more detail in the image than even the best of the old-timey film cameras. And the other thing, and you can see it over here as an example of, some different images. So here's an image being seen by a CCD, and you can see there are lots of zeros over here, and then there's some numbers representing the different intensities in this image. The higher the number of pixels per area you have, the more resolution you get, the sharper the image will be. But mainly what I want you to get across is this idea of what it means for something to be a digital image. And the great thing about digital photography is you have all these numbers that you can process with computer algorithms. And you can use these computer algorithms to basically do software manipulation to improve the image, to improve the contrast, or to make it more clear. I mean, you guys know the kinds of things you can do in Photoshop, not making things up or adding things, but just making the picture look better. And so these are the kinds of things that you can do with digital cameras, and it really has been a boon to astronomy. So here's the kind of image processing that computers can do to sort of sharpen images. And so you might be looking at a really, really dim image, and so that's not got a lot of good resolution, but there's a lot of noise in here, and it's sort of distorted the image, so you can't really tell what's going on. But you can do computer processing, and that computer processing can turn that image into something that's got more structure and more detail, and you can kind of see, actually, oh, there's stuff going on there. And similarly, on this image here, you can sort of see that sort of effect. So you can go from an image that really you can't really tell much about it to one where you can see a lot of detail and a lot of structure and reveal a lot of information about what you're actually seeing there. Now, as I mentioned, there is a problem that when your telescope is on the ground, the light coming from outer space has to pass through our atmosphere. And in our atmosphere, there's dust and dirt and turbulence, little places where the air is a little bit more dense and places where it's a little bit less dense. This can affect the quality of the light, and so you sort of get all these wiggling from the air moving around, causes the light to sort of wiggle back and forth. And so what we want is we want the light to come in as parallel rays, but as it passes through the atmosphere, it kind of wiggles back and forth. So when the light actually gets to the telescope, this ray of light might be wiggling one way and this ray of light might be wiggling another way. And so instead of all these parallel light beams coming to a nice sharp focus by the lenses in the telescope, they might come to a little bit more of a blurry focus. There are some things that astronomers can do to kind of counteract that effect. They can make use of what's called active optics and adaptive optics. Now, active optics basically means you control the mirrors based on temperature and orientation. Now, both of these technologies are sort of used to adjust the shape of the mirror that's in the telescope. One of the problems with mirrors is that they have to be exactly the right shape to work properly. But you guys know that, for example, if I put a piece of metal out in the sun, it's going to warm up, and what happens to it is it's going to expand. It's going to stretch out. And this can actually happen to mirrors as well, these large mirrors in these big telescopes. Different temperatures and different conditions can cause the mirror to be deformed, and so it doesn't perform correctly. And so astronomers want to prevent that. And the problems get more pronounced the bigger the mirrors are. And so this actually put a limit on how big the mirrors in a telescope could be. But astronomers figured out how to get around this using what's called active optics, where instead of one giant mirror, you make a mirror that's made out of smaller segments, and you can control the shape of each of these individual segments. And so if the temperature change causes some expansion or whatever that deforms the mirror, you can control the shape of these segments to sort of realign it. And that is what active optics is and does. Now, adaptive optics takes the idea of active optics and puts it on steroids and then interfaces it with a computer. So you can actually, remember we talked about how when the light comes in from a star or whatever, that light is being distorted by the atmosphere. Well, what you can do is you can take something like a laser and you can track how a laser beam changes as it moves through the atmosphere, and you can use that information to sort of manipulate the mirror in real time, so that if a particular beam of light is wiggling at a certain angle when it comes into the mirror because of these atmospheric distortions, you can sort of change the shape of deform that mirror to undo that mistake. And so this is a way that you can actually sort of minimize or reduce those atmospheric distortions tremendously to improve the quality of the images in the telescope. It's really a very cool thing if you think about it. So again, here are some images showing the sort of improvement that's possible by looking at adaptive optics to sort of improve the quality of the image. Now, the next thing I want to talk about is radio astronomy, and that's using radio telescopes. Now, radio telescopes are basically big antennas. Like, you have an antenna built into your car that enables you to pick up radio signals from the radio station. Well, radio telescopes are basically these giant antennas that are designed to pick up radio signals coming from outer space. Things in outer space don't just make visible light. They make the entire spectrum. They make infrared light, they make ultraviolet light, and of course they make radio waves. And so in order to get a full picture of what's out there, we need to be able to look at all the different parts of the electromagnetic spectrum and see what information is there. And it turns out radio waves are one of the key areas of the electromagnetic spectrum that we can see a lot of astronomical information from. And if you remember, we talked about those atmospheric windows in a previous chapter, that our atmosphere actually blocks out a lot of the infrared and ultraviolet light, so we can't actually see those portions of the spectrum from the surface of the Earth. But radio waves can get through the atmosphere, so we can have ground-based telescopes that look not just at the visible light, but at an entirely different portion of the spectrum. In here, you can actually see a picture of a radio telescope. And here you can see down below is a building. So, I mean, these things are absolutely gigantically huge. And the reason that they're so big is because if you remember, I showed you a slide previously showing the sizes of different parts of the electromagnetic spectrum. That is the size of the wavelength. And for the radio wave part of the spectrum, the wavelengths could range from the size of a person to the size of a mountain. And so, that's why these things are so big. They want to be able to accommodate a large range of radio frequency wavelengths and be able to focus them so that they can be seen. And so you can see actually this sort of schematic over on the side. You've got radio waves coming in, they reflect off the mirror, and then there's this sensor up above where they focus. So this is basically just a mirror-based telescope, but instead of designed to reflect visible light, it's designed to reflect and focus radio waves. Now, this is, or I should say was, the largest radio telescope in the world. It was built into a crater on the island of Puerto Rico, and it was the radio telescope at Arecibo. And you can see the dish here, and you can see the sensors up above. Unfortunately, during the COVID pandemic, the telescope wasn't maintained, and it suffered a catastrophic failure. And the cable snapped and it actually collapsed, and so it's been decommissioned. So it no longer functions, but it was for many years a marvel of radio astronomy and produced a lot of great data. Now, why do we care about radio astronomy? Well, there are lots of different things that we can do with it. It has advantages, but it also has some disadvantages. Now, one of the disadvantages is that longer wavelength, it means that you get poor angular resolution. Remember, we talked about the resolution of a telescope, and we said that it depended on how big the telescope was, but also the wavelength of the light. And because the wavelength of radio waves is so long, you get terrible angular resolution. Even though these telescopes are really big, the wavelength is so much bigger even still than, say, the wavelength of visible light. It's not even in the ballpark. And so you get very poor angular resolution from these radio telescopes. Now, it turns out, we'll see, there's something you can do to fix that. But to just have one of those big old radio telescopes, you're going to get really bad angular resolution. Remember, what that means is that if you see two objects that are close together, you're not necessarily going to be able to tell whether it's one object or two objects whose radiation is all smeared together. But even if that's a disadvantage of radio telescopes, there is an advantage. There are multiple advantages. One is that you can observe 24 hours a day. With a regular telescope, you can't observe during the day. You can only observe at night, because during the day you can't see any stars, right? The sky is blue, there's too much light from the sun washing out everything else. But with a radio telescope, you're looking at an entirely different part of the spectrum, and it goes straight through without any problems whatsoever. And so you can observe 24 hours a day. Also, if you want to do astronomy with a visible telescope, with an optical telescope, you can't do it if it's too cloudy. You can't see through the clouds. But radio waves can pass through clouds. They can pass through rain and snow. So those things don't interfere with radio telescopes. So those are some neat advantages that radio telescopes have over optical telescopes. And of course, you get observations at an entirely different frequency range. So you get totally different information. So if you just had radio telescopes, you wouldn't see the full picture. If you just had optical telescopes, you wouldn't see the full picture. But by having both of them together, you see more of the full picture than you would see having just one or the other. Now, I mentioned that there was a disadvantage, that poor angular resolution. How can we fix that? It turns out that you can use something called interferometry. And what that does is it combines the information from several telescopes that are spread out, and it combines it in a way mathematically so that the signal looks like it comes from one giant telescope. We can think about it like this. You can see these telescopes here. So if I've got a telescope, there, I'm trying to, draw these kinds of telescopes. The area of each individual telescope is pretty small, but by combining the signals from each one using mathematics, I can make it as though I'm looking with a telescope that has a dish that big. And so remember, the spatial resolution depends on the wavelength, but also how big your dish is or your mirror is. And so it's a kind of a way of cheating. So remember, these individual guys are really, really big themselves, but by combining in this way, you can create effectively a giant telescope. And basically the way they do this is each telescope is getting a slightly different image because it's at a slightly different position, and they can mathematically combine those signals in a way that enables them to treat it as though it was one telescope covering a larger area. In here you can sort of see the kind of improvement that you can get. Here we have an image that is taken from an array of radio telescopes up here, and you can see the corresponding image. So this one is, the little legend tells us this one is in the radio part of the spectrum, and this one is in the visible part of the spectrum. Now, you can see the visible part of the spectrum has a lot more detail, but the resolution of the radio spectrum is not as bad as it would be as if it were just a single radio telescope. So that's kind of a cool thing.